All right, so we're going to talk about hybridization and sigma bonding. First of all, quantum mechanics has all this math that's involved, and it has a lot of good stuff involved with that. But they have, as part of their mathematical equations, determined shapes for different orbitals. The s orbital is a sphere, according to this mathematics. The p orbital is going to be what they call a dumbbell shape. So, there it is. It's going to be on the x-axis, it's going to be on the z-axis, and it's going to be on the y-axis. So it's going side to side, it's going up and down, and another one is coming in and out. And so these p orbitals would have a 90-degree angle to each other, and that s would just be in the middle. So this again is backed up by math, which has also helped with doing things, looking at the universe and stars and stuff. So quantum physics works in a lot of situations, and I'm just not smart enough to understand it completely, but I go with it. Anyway, so the question becomes, how do we get these 109-degree bond angles if this is 90 degrees and that's 90 degrees and that's 90 degrees, and then this isn't even any degrees, it's just in the middle? The theory goes that you throw them into a hybridization machine. So, sort of, if you've ever watched Dora, that Fix-It machine, if you take the S and the three P's and you put it in there, it will spit out four equivalent orbitals that are in a tetrahedral orientation, and we call that the hybridization. And since that hybridization involved an S and three P's, we would call that an sp3 hybridized situation. So, for example, like CH4, carbon has two electrons in the 2s and two electrons in the 2p. It would put one of those electrons into the 2p, so it has one electron in each, all spinning in the same direction. Stick that in the hybridization machine, and your S and your higher energy 3p's would become equal energy sp3 hybridized. And then those hybridized orbitals would be in a tetrahedral shape, and that tetrahedral shape would then be able to take a hydrogen on each one and form a tetrahedral CH4 molecule. All right, so you may say, well, wait a minute, didn't you tell us there's things that have more than four areas of electrons around them, like the phosphorus pentachloride and the sulfur hexafluoride, the trigonal bipyramid and the octahedral shapes? And the answer is yes. If you have access to D subshells, so if you're in period 3, 4, 5, 6, you have an empty D subshell available to you, and that allows you to expand beyond the 8 electron domains around your atom. So we see that for anything, mostly since we're talking about nonmetals. So you're looking at these down here, this area. So that weird stuff with xenon is available because it has this D, right? It has the 5D available to it. Um, bromine, silica, well, sulfur, as you can see right here, has a 3D open. Phosphorus would also have a 3D open. So these all have availability to dive into the D. And just like when you have much family coming and you got to get that card table out of the attic and bring it down and have some people sit there, the S and P is able to grab one of these D orbitals and hybridize that as well and make it into 5 equivalent sp3D so that the chlorines can all fit. So at the end of the day, here's what we know. Electron domains are areas around the central atom that have electrons. That includes unshared pairs as well as bonded pairs. And we'll take looks at this. It'll make more sense when it's a picture. If there are two electron domains, then you only need two areas for electrons. So you're going to take the S and then one P. And you're always going to take the S and then whatever else you need. So it's S and P. If you have three areas of electrons, you're going to take an S and 2P. If there's four areas, you're going to take the S and 3P. But now we're out of P orbitals. So if we need 5, we got to get into the D. And if we need 6, we're going to get sp3d2. So more in the way we learned it, if you have two areas, right, this carbon has two areas of electrons around it, so it's going to be sp hybridized. This oxygen has three areas around it, so it's going to be sp2 hybridized. But anyway, So that carbon's going to be sp hybridized because the electrons are occupying only two areas around it. The boron in BF3 has three areas of electrons around it, so it's going to need the sp2. That would also be true for like formaldehyde, where there's a carbon double bonded to an oxygen and two hydrogens. That would also be sp2 hybridized because there's only three areas of electrons around CH2O. All right, water, ammonia, anything with four bonds in the carbon things, right? So methane, anything, anytime carbon's making those four bonds, most nitrogen things, I want to say most because you never know, but should be most nitrogen things are going to bond three times. Oxygen's going to bind the two times with the two lone pair, and nitrogen's going to have that other lone pair. So these all need to be sp3 hybridized because there's four areas of electrons around that central atom. And then for the crazy ones, sp3d for the things that have five areas of electrons around them. So your teeter-totter shape, your T-shapes, your um, trigonal bipyramids, and then your octahedral or your square planars or your um, square pyramidal, all those that have six areas of electrons around them are going to need that to be sp3d2. So moving into what happens next, if we have sp2 hybridized boron, that means it has a p orbital that's empty and it's just going up and down and there it is. And so that actually allows boron to act like an acid. It can occupy a lone pair in this p orbital. We'll talk about that more when we get into acids and bases. But if you're thinking about um, carbon and oxygen here, when it's in formaldehyde. So here's formaldehyde. Carbon is sp2 hybridized, has three areas of electrons around it, as does that oxygen have three areas of electrons around it. So that's sp2 hybridized. So there's three equivalent sp2 hybridized orbitals, but both the oxygen and the carbon have this empty p that is perpendicular to the plane of everything else. So those perpendicular orbitals will overlap and form that double bond. So the double bond happens by forming with that empty p, or a half-filled p, I guess, when we really think about it. Each of them has one electron in there, and they're going to overlap above and below the plane of the nuclei. And we call that a pi bond when that happens. A sigma bond happens between the nuclei, and then a pi bond happens when that space is already taken between the nuclei. So the pi bond has to form around that real estate that is the shortest distance. So here we see the C2H4, sp2 hybridized carbon, sp2 hybridized carbon. They're overlapping with the S's of the hydrogens and the S's of the hydrogens and with each other. But each of these carbons has an empty p. So if we sort of rotate this 90 degrees so that it's now going in and out of the screen, you can see that the p orbitals, which would be like right there coming out and right there coming out, are now above and below, and they can overlap and make that double bond. So when you see C2H4, you have those 1, 2, 3, 4, 5 sigma bonds, right? That's the, oh yeah, you're right. I can't go backwards on these. Love that. Anyway, you have your 5 sigma bonds and then the 1 pi bond. With oxalic acid, you have the first bond between two atoms is always going to take that space between the two nuclei. So they're always going to be sigma. So that's a sigma, 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 and that's a sigma. So that's 7 sigma. That's going to be a pi because the one sigma already existed. And the other one here is going to be a pi because one sigma already existed. So you got 7 sigma bonds and 2 pi bonds in that structure. And if you think about it with like HCN, right, first bond between atoms is sigma. This carbon has to make 2 more bonds to get a total of 4. So it's going to go above and below and make a double and a triple bond with that nitrogen. The double and triple bonds, right, are always going to be pi bonds. So this has 2 sigma bonds and 2 pi bonds. And again, if you think about on this, um, looking from this angle, so looking at this from the top, there would be a p orbital going out and back, and they're going to overlap to make a pi bond. And then when we rotate that 90 degrees so that this plane is now coming in and out of the screen, there'll be another p orbital going up and down, and they'll overlap and do that second bond. So the two multiple bonds, the double bond and the triple bond, are happening in a space that's not in the direct line between the nuclei. They're happening above them, below them, and in front and behind it. And that's what a pi bond is.